Okay, hello everyone. In the previous lectures, we started to learn about automatic program repair techniques, including general purpose and special purpose program repair techniques. In this lecture, we will continue to learn the techniques for automatically fixing either specific bugs like null pointer reference error or generic software bugs. Okay, let's start with the second lecture of the automatic program repair techniques. In today's lectures, we will continue to learn the state-of-the-art techniques for fixing memory deallocation errors such as memory leak and double free and ejector free. So all of these techniques have been published at top conferences in software engineering and belong to the special purpose program repair techniques. So let's start with a quick review of what we learned last week. At last week, we start with why we need APR techniques. First, the half of the total software development time was used for debugging. And some papers reported that it takes an average of 200 days to correctly fix a single bug in commercial softwares. The second reason we need to APR techniques is that the number of software bugs keeps increasing every year. For example, just for fun, if the number of bugs reported on CV at last year was about 18,000 and it took 200 days to fix each bug, then it'll take about 10,000 a year to fix those bugs. The third reason why we need to APR technique is that fixing errors manually by developers is very time-consuming and error-prone. For example, record the process of fixing the double free error in the Linux kernel we have learned the last week. The developer is not only hard to be sure whether this original bug is fixed, but also easily introduce a new bugs during the fixing process. This is why we need the APR techniques. For this reason, APR techniques are being actively studied from the academia and industry. As we learned before, APR techniques are classified into general purpose and the special purpose program repairs. First, the general purpose repair techniques aims to repair all types of errors, but these techniques may have poor performance in fixing some specific type of errors. On the other hand, special purpose program repair techniques is specialized for fixing the specific kinds of errors. So these are not generally applicable for fixing other types of errors. In particular, we have learned MemFix, which is the state-of-the-art techniques for fixing memory deallocation errors. And to fix the bugs, the first key idea of the MemFix is to enumerate all the object traces by using a static analysis. More specifically, they use the variant of type state analysis for tracking all possible deallocation statement for each object. Second key idea is to transform finding a set of safe deallocation statement into solving an exact cover problems where the solution corresponds to a correct patch for this box. This is what we learned last time. Now to start with this week lectures, let's see the performance of MemFix first. MemFix used for 24 programs belong to the GNU core utils for the evaluations. More specifically, they evaluate whether the Mempix was able to generate a safe and correct patch for those programs with all free statement deleted. And they compare the performance, which is the fixed ratio of the Mempix with the one of the leakfix, which is another state-of-the-art APR techniques for fixing memory leaks. As you can see, Mempix was able to fix half of all programs, while leakfix managed to fix about 13% of the programs. That is, Mempix succeeded in increasing repairability a lot compared to leakfix, but looking at the line of the code used for the evaluation highlighted in the red, this shows that Mempix has scalability issues. The line of the code Mempix used ranged from about 500 to the 35,000 line of code. Okay, let's evaluate the diverse state-of-the-art techniques for fixing memory deallocation errors in the 4 aspects. The first aspect is the scalability, which is how large programs each technique can fix. And the second aspect is the safety, which is related to whether each technique does not introduce new errors during the process of the fixing. And the third aspect is to correctness, whether this technique correctly fixed the original bugs. And the last aspect is the repairability of how many errors this technique can fix. Okay, let's look at the Mempix first. We can see Mempix as a APR technique for focusing on safety and correctness. So as a result, the generated patches by Mempix guaranteed to fix the original error without introducing new errors. However, in order to guarantee these 2 aspects, which is correctness and safety, Mempix sacrificed the scalabilities. So this technique only works for the programs having about 3,000 code lines. What about the leakfix? Leakfix is a technique focused on scalability and the safety. In other words, this technique works even in the large programs such as hundreds of the thousands of lines codes. And it is able to generate the patches without introducing new errors. But similarly, leakfix sacrifices the ability to fix the original errors. And as a result, leakfix is inferior to Mempix in terms of the correctness and the repairability as well. How about the foot patch released at ICSI 2018? This foot patch focused on scalability while trying to take all the other 3 aspects. As a result, these patches generated by foot patch may not fix the original error or can also introduce new errors. Lastly, I will introduce the most recent technique, with the tool name is Saber in detail. As you can see, compared to the 3 techniques mentioned above, Saber has overall stable performance in all the 4 aspects. In particular, like Mempix and leakfix, the generated patches by Saber also guarantees to generate the patches without introducing new errors. First, at a high level, let me explain the usage scenario of Saber. Saber first takes the program under test as an input and then generate the error report of the program by using static analyzers such as Infer, which is developed by Facebook. For example, this static analyzer Infer reports a possible memory leak at line 10 in the main function of the programs. And then Saber aims to generate the safe patches by using this error report and the programs. As a more specific examples, suppose that Saber takes the open source program named Snort with about 300,000 lines as an input and tries to automatically fix the programs. Let me explain first the simplified code snippet of the Snort programs. First, look at the for loop from the line 8 to 11, line 11. And as you can see, this loop iterates over the linked list LX. And for each iterations, a data object is allocated in the line 9. And the data of the current node is copied to the allocated object at the next line, and the copied data at the line 11 is appended to the list ly through the function appended data. And let's look at the function append data. This function returns 0 if the data is successfully appended to the list ly. On the other hand, the function will return -1 when the data fails to be appended to the list ly. Okay, this static analyzer Infer will generate the error report that the object allocated at line 9 is unreachable at line 11, where this report is a true alarm. So Saber takes this error report and the original Snort program as input, and it generates the following patches highlighted in green. Fixing this memory leak error is tricky because we should insert the freeze statement when the appended data function fails to save the data. So we should insert the freeze statement only when the return value of this function is -1. However, Saber successfully takes about 300,000 lines of code as input and succeed in fixing this memory leak error report correctly.